In today's video, we're going to look at emission spectra, what causes them, what you can do with the information from an electric spectrum. On screen is the virtual learning lab. This one is based on a simulation. But if you did the in-person lab where you got to see the actual tubes of light, still pay attention because there's information that will help you complete your lab, including what causes the emission spectrum, but also how to calculate the different variables from the spectrum. Now, in this particular case, we didn't have an easy simulation to use. We're using a shear PG or PJ. It takes a moment to load on your computer, so when you click the link or type in and get to the page, it will take a moment for this simulation to show up. According to the instructions, we're going to go to multiple atoms. And so in this particular case, we have a lot of atoms of hydrogen. So I'm going to push play. Now coming out of the left side are little blue dots, and they hit the atoms, which then you'll see that the atoms have this little circle around them. What that's telling us is the electron is giving some of its energy to the electrons inside the atom. But then we'll notice once that circle disappears, then a colored star comes out. That's light. So let me just go over that again. Electrons with energy hit the atom. The atom gets excited. The electron, one electron inside that atom, could be more, but usually just one electron, gets excited, and then it releases that energy as light. Now, electrons are not destroyed in this. It's just simply that the electron that came from the left side has given some of its energy to the atoms. So inside the atom, we have this model here. Electrons like to be at their lowest energy level. That's what we learned in chemistry class. So that's this bottom line here. When an electron with energy hits the atom, it gives some of its energy to one of the electrons inside. That's what makes the circles around it. And the electron pops up. Now you see most of those electrons will pop up to number 2, but you occasionally see a 5 or a 6. That's a higher energy level. So an electron can give its energy to an electron inside the atom and cause that electron to jump up to the second energy level or one of the other ones. But it can't stay there. The electrons can't stay at these upper energy levels very long. So they pop down. That's why they keep disappearing. And when they do that, they release light. Since the energy levels are actually different, the light is different. Meaning, depending on which energy level it goes from and to, that will determine the type of light that comes out of it, because light is energy. So if we looked at the spectrometer down here, we'll see that we're getting a colored dots. UV isn't a color, so that's why it's gray. Infrared isn't a color, so that's why it's gray. But we see we get red, this sort of bluish green, blue, and purple. So if you were to see this in person, these would just be tall bars here, just be consistently tall bars. But what we're using in this computer simulation is sort of like a scatter graph where it's like, oh, we get the red, we get more red, and then purple a little bit later with the blue-green and then blue. So these are less often occurring. But whatever, we still get the overall idea that the light is actually coming from the electrons. So these lines here, we can argue about, is this purple or violet? But in reality, physics isn't about the specific color name. Rather, we can measure this light in terms of wavelength and frequency, and that means something. So this purple one here versus the blue one, the purple one has a smaller wavelength. It looks like it's just a little past 410. Let's see, 10, 20, 30, 40. So this one is 435 nanometers. So 435 nanometers. So the blue one has a larger wavelength. The purple one has a higher frequency. So those represent physical quantities. Now, frequency is directly related to energy, so that means that the purple one, since it's more frequent, will actually have more energy. Purple has more energy than blue does. So these correspond to the changes in the electron jumping down from a higher energy to a lower energy. So this emission spectrum is unique to hydrogen. If we were to try this with a different element, it would have different placements of electrons, different amounts of electrons. So here's mercury. We have most of the electrons down on the lower level as expected, but the energy levels you see have been squished together, and there's way more of them. So we're starting to see some colors coming up, and they're different from what we saw before because the placement of the electrons is very different at Mercury. It has more electrons, more orbitals that electrons can go into. So there is a bit more going on here. We do get a purple and a blue, but now we get sort of a greenish yellow and a yellow, and definitely some ultraviolet and infrared. If you were in person, you could only see the ones in color. You couldn't see the ultraviolet or the infrared because human eyes cannot see these colors. So if you were doing your virtual lab here, you can see that I've cut and pasted the spectrum, and you're just going to draw the colors here. If you don't have a coloring device, you can just label the colors, but you want to get the relative amounts of wavelengths in there because those correspond to the wavelength, frequency, and energy. And then you'll just repeat that with mercury, sodium, and neon. If you were in person, you should have seen the spectrums and drawn them on your own papers. And again, you get to see the specific colors. It was more difficult to measure wavelength. So if you're in person, you're not as precise about wavelength. So that's part A. Let's move to part B, which is measuring or calculating. So I'll let people do part B 1 through 4, and I'm really going to jump down to the math of 5 through 8, and that'll help us with later questions. So in question 5, we're given wavelength, and we have to calculate frequency. So I put in a practice problem here. It says calculate the frequency of a 750 nanometer wave. So what do we know? Well, we know 750 nanometers, that's wavelength. And our question is to find frequency. So we have to have a formula that includes both frequency and wavelength. So I think the easiest one to do, I can't type it because I can't put this lambda symbol in the keyboard. So the most common formula that we could go to is V equals F times lambda. That's the one you're most often going to find. Unfortunately, it's not solved for lambda, so we do need to do some work. So I have V equals F times lambda. To solve for frequency, I got to move the lambda. So I'm just going to divide by lambda. And my formula turns into frequency equals V divided by lambda. Now, if I type the numbers in, some of you might be thinking, I don't know V. Well, if you're not given a velocity, and you know you're talking about light, then you should just use the speed of light in a vacuum, which is c. So hopefully you know that. I'm going to type it on the screen. If you don't know it, then you should write it down. So it is 300 million meters per second. And that is divided by wavelength, which is 750 nanometers. Now the problem with this is it is set up correctly. We do have velocity over wavelength, but we'll notice we have meters up here and nanometers down here. That's not going to work out in our favor. It's going to make a messy number. So we do need to convert it. So nano means e to the minus 9. I even put it up here in the problem. So when we're typing this in our calculator, let's remove the n. Oops. 750 e to the minus 9 meters. So removing the n means that we're putting in e to the minus 9. So when you plug that in your calculator, you just need to make sure you're pushing those buttons. So let's see, I'm going to pull up my calculator. So our E button for this calculator is the double E. This is very similar to the iPhones. Okay. So I have 300 million. I don't want to type in 8 zeros, so I'm going to type in 3E8. I don't like that this is lowercase because it really should be uppercase because you don't want to use that button. You want to use the capital double E button. So here's my 300 million. There we go, see all the zeros. I hit divide by, I'm going to type in 750 E negative 9, not subtraction 9, negative 9. Holy goodness, that's a lot. Okay, so this is a pretty big number, but that is actually the frequency of this light. Now I can type in 4 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros after it. 4 with 14 zeros after it. Or I can write E 14 hertz. Because remember that E tells us how much the decimal has been moved. Since our value is bigger than 1, it's going to be a positive E, and it got moved 14 places. 3, 6, 9, 12, 14 places. So there's our answer for this particular question. So if you're doing this particular problem with your own values, you would just plug in your own particular wavelength here, remembering if you have nanometers, which often you do, you'll need to convert that into regular, which is e to the minus 9. So now we're going to calculate the energy of that wave. So the formula for that is E equals H times F. So H happens to be a constant. It's called Planck's constant because that's the person who did a lot of work on it. And then we're going to multiply it by frequency, which we are going to get from our previous problems. We're going to look back on the above problem. That's our F, so we're going to need that number. We are not going to use the 750 nanometers because that's wavelength. That's not frequency. We don't want that. So I'm just typing in the number for H. This is a constant. Every time you use this equation, you have to have this number, 6.63 e to the minus 34th joule seconds. So the JS represents units. And when you multiply by hertz, the hertz and the seconds will cancel out. So you'll end up with just joules, which is energy. And that's kind of the point. There we go. So again, whenever you're using this formula, you have to have H. And in this case, we're solving for energy, so we just need to simply multiply that energy by the frequency we got in the last problem. And if I'm careful, it's still in my calculator. So there we go. It's still there. So I'm just going to multiply it by H times 6.63, capital double E, negative 34. All right, so that number looks pretty small, but it's the energy of one photon. So, you know, if you have a gas sample, you probably have a billion, so then it's probably okay. So 2.652 e to the minus 19. So remember, they're showing a lowercase e, but it really should be capital E. And then the units for that are joules. So that is the energy of one photon of a 750 nanometer light. We're not using the 750 because that represents wavelength. Instead, we are just multiplying the frequency times the energy. So that's it for our video. Please let me know if you have any questions.